All right, we've looked at how we name alkenes. When we encounter double bonds, they actually lead to the possibility of a specific type of phenomenon resulting in your organic compound, and that is the possible existence of a special type of isomerism or isomers known as cis-trans isomers. And you'll see the term cis-trans or geometric isomers used interchangeably in your textbook and online and elsewhere. They mean the exact same thing. Now, the reason why this type of isomerism exists is because when you have a double bond in an alkene, that double bond is very different than a single bond. Okay, so remember or recall when we looked at the first part of the chapter, single bonds can easily rotate. And they can rotate around very easily. When you have double bonds, the double bond is very rigid and it does not rotate, right? So it prevents rotation of the connecting or the connected bonds. So what that means is that the atoms connected are locked in place. And that leads to this special type of isomerism known as cis-trans or geometric isomerism. So it results in cis-trans isomers. Okay, and to help you sort of remember what this actually means, all right, we'll use a little bit of alliteration here. So we can say cis means on the same side of the double bond. Right, so we can say cis on the same side, right? So we're going with the S's or the S sound. So cis on the same side, trans would be on opposite sides. Of the double bond. All right, so I'll just show you a pretty simple example here. So we have a compound, and I'll just draw the structure out. So we have two carbons connected by a double bond, and then we have a Cl on one and a Cl on the other, right? So if you were to name this, right, two carbons in a row, that makes it eth. It's a double bond, so ethene, and we have two chlorines attached. So, and they're both on carbons 1 and 2, so 1,2-dichloroethene. But now because of the double bond, right, what can actually happen is we have a couple possibilities, right? Both of the chlorines can be on the same side of the double bond, in which case we use another prefix here, cis, right, on the same side. Or one chlorine can be on one side and the other on the other side of the double bond, and these now are trans to each other. So we say that's trans 1,2-dichloroethene. All right, so when we use the double bond as a reference and we say on one side or on opposite sides of the double bond, we're looking here as at the bond between them as our point of delineation. All right, so the one on the left here, both chlorines are on the top, right, on the top side, so they're on the same side, so it's cis. And here one chlorine is above, the other one is below, so we call it the trans isomer. Right, that's one thing that you really have to pay attention to when you have double bonds in a molecule. When it's an alkene, you have to look at the possibility of the cis-trans isomerism. Right, there's a little analogy you can use using your thumb and your fingers. to help illustrate that point of what cis and what trans actually mean. So your pointer finger and your middle finger can make up that double bond, and then your thumb would be the things that can be either cis or trans to each other. Right, so if they're both pointing up, that means it's cis. If you switch one, you'll see that they're trans to each other. All right, so we'll take a look at another simple example here of where cis-trans isomerism can exist. And we'll first of all start and take a look at where cis-trans is not possible. All right, so if you take a look at butene, all right, if you were to draw this structure for butene, right, and you were to name it, right, so it's 1, 2, 3, 4. All right, so that's butene. And then the double bond starts on carbon 1, so it's 1-butene. So the question is, right, we have a double bond, which means we need to look at the possibility of having a cis or trans isomer. Now, in order for cis or trans isomerism to exist, all right, and we should write that up here, in order for cis-trans to be possible, the groups or atoms attached to each carbon of the double bond must be different from each other. Okay, so what do I mean by that? Well, let's take a look at the 1-butene. All right, and let's draw out this structure a little bit in more detail. So there is my double bond. So I have a carbon here, I have a carbon there, and then I'm just going to draw out the carbons, and then we'll draw in the H's as well to kind of illustrate this point. All right, so the carbon on the right, there's 3 H's, so we'll draw those in. Carbon in the middle, there's 2 H's. This carbon here on the left side, there are 2 H's. And then the second carbon here, right now it's got 3 bonds, a double and a single. So there's 1 H remaining. All right, so what we're saying is, in order for the cis-trans to exist or to be possible, the two groups attached, or the 2 atoms attached to each of these carbons, have to be different from each other. So let's take a close look at that. What do we have attached to carbon number? This is carbon 1, and that's carbon 2. So to carbon number 2, we have an H, and we have an ethyl group attached to it, right? These two are different, which is great. But then both things, or both atoms, or both groups attached to this carbon also have to be different from each other. Well, what do we have attached to that carbon? We have an H, and we have another H, right? So these are the same. So if they're the same, that means no cis-trans is possible, right? Because both groups, or both atoms attached to each of the carbons in the double bond have to be different. So when you name this particular structure, right, it's just 1-butene, it's not cis or trans, because there's nothing to be cis or trans to in that structure. That's different, though, than if you had something like 2-butene. All right, so if I have something like this, right, so there's my 4 carbons. All right, so this we know now is 2-butene. So there's 1, 2, 3, 4. And I'm just going to draw in the H's for right now on both of the carbons that make up the double bond. So there's an H here, and there's an H on that one. So if I compare what's attached to each of those carbons, I can see on carbon number 2, there's an H, and then there's a methyl group. And these are different from each other. And on carbon number 3, right, there's an H, and there's a methyl group, and these are also different from each other. So that means that there is now the possibility of cis trans. So if I look at my double bond right here, right, I can see that the H's, for instance, are on opposite sides of the double bond. So I'm comparing these. So that would make it the trans isomer of 2-butene. And that's different than if I had something like this, right? So there's my carbon 1, 2, 3, and 4, right? And again, if I draw in the H's attached to each of my carbon of the double bond, I have an H here, and I have an H on that carbon, right? Again, attached to carbon 2, I have a hydrogen and I have a methyl. These are different. On carbon 3, I have a hydrogen and I have a methyl. These are different from each other as well. Right, so there's a possibility of cis trans. I look at my double bond. There it is. I orient myself. My H's now are on the same side. So this would be cis 2-butene. Right, it may not seem like a big difference. It may seem like a slight difference. But it can actually have really big consequences for the shape of the molecule and its function down the road, right? So for example, a lot of insects and organisms emit different compounds, different molecules that they use to attract, mates, for instance, for the propagation of the species. And in lots of cases, these compounds called pheromones are either in the cis or the trans isomer, and having one versus the other either leads to attracting a mate or to not attracting a mate, right? So it's extremely important, not just in the case of these insects, but in the case of making drugs, for instance, right? So why is one drug particularly effective versus another one? Well, sometimes it may have to do with the structure, right? Maybe just having one bond in a cis versus a trans can have a huge impact. And when we get to our lipids and fats down the road, we're going to see that this cis-trans idea has a huge impact on the health or the benefit of things like, and you probably have heard this term in the news, and if you follow diet and that general thing, trans fats, right? So that term trans actually has to do with the double bond and how the groups are oriented relative to that double bond. All right, so let's take a look here at a couple examples. We'll just do the one in the middle, option B. All right, so as with anything, here we have a chain. So let's get the longest continuous carbon chain. So we'll start on one end. That's 1, 2, 3, 4. And if I start on the other side, I go 1, 2, 3, 4. 4 is going to be the longest. All right, so I have 4, that's but. It's a double bond, so it's butene. The double bond in either direction starts on carbon 2. So that's 2-butene. All right, so now I look at the possibility of cis or trans. So I focus in now on what's attached to each carbon of the double bond. So on carbon on this one, right, I have a bromine and I have a methyl. They're different from each other. And when I look at the other carbon, that one, I see that there's a methyl and a bromine. These are different from each other as well. Right, so there's a possibility of cis or trans. Now I look and I see, I can compare, for instance, the bromines, and I can see that these bromines are on opposite sides of the double bond. Opposite sides would be trans, so this would be trans to butene. But don't forget that we also have bromine in here, right? And they're on carbons 2 and 3, right? So we did forget that it's 2,3-dibromo that we forgot to include in the name. All right, so let's go ahead and incorporate that because we did forget. So the trans goes at the very front. 2, 3 dibromo 2 butene.